Thanks for everyone for showing up, coming here, and we're very happy to have Ciprian Manolescu, who will talk today about a not Floer stable homotopy type.
Okay.
So, go ahead.
Thank you very much for the invitation. So I will talk about joint work with Shar-Kar. And this is mostly low-dimensional topology, but we're trying to imitate symplectic geometry. I will try to emphasize the symplectic aspects. Okay, so let's just start by reviewing what Flur homotopy theory is. So this is a general program to construct spaces, or more generally stable homotopy types, whose homology is Flur homology. And the idea first came in a paper by Cohen, Jones, and Siegel in 1995, where they sketched the general procedure. I will go over it a bit later. Then there was work by a bunch of people. I started in 2001 in the Seiberg-Witten context. So we're constructing the Seiberg-Witten Flur homotopy for 3 manifolds. Then Ralph Cohen explained the Hamiltonian Flur homotopy type of T star M. Lipschitz and Shar-Kar did something for Hovanov homology. They upgraded it to a homotopy type. That's not quite Flur theory, but it's very similar. And what we do will be inspired by what they did. More recently, Abu Zaid and Blumberg proved the Arnold conjecture over FP using Hamiltonian Morava K theory. And there's more versions of Flur theory. There was a program at MSRI/SL Math last year on this subject. Okay, in this talk, I will discuss upgrading link Flur homology to a stable homotopy theory. So first, let me tell you what link Flur homology is. It's a version of Heggard-Flur homology. I will discuss the combinatorial version, which is associated to grid diagrams for links. And that takes the name grid homology. There's a book on this subject, but it's the same as the older link Flur homology, which comes from symplectic geometry. So knot Flur homology, the version for knots, was constructed by Oshwart-Szabo and Rasmussen in 2003. It's a bi-graded homology theory for knots. There are different versions of it, which have the symbols hat, minus, plus, and so on. And its Euler characteristic is the Alexander polynomial. Then Oshwart and Szabo extended it to links, and that takes the name of link Flur homology. It's an important knot invariance. Now, there does a lot of work on it by now. It detects, for example, the genus of the knot, the minimal genus of a surface whose boundary is the knot. It can be read, if you know knot Flur homology, it's the maximal S such that H of K is non-zero in degree S, in the second degree being S. More applications. It also detects if the complement of the knot fibers over S1 by telling whether in the highest degree, which is the genus of the knot, the homology is Z or not. Using these properties, you can show that it detects the unknot, the trefoil, and the figure-8 knot, meaning that if a knot has the same homology as, say, the trefoil, then it is the trefoil. It doesn't detect all knots, of course. There are knots with the same knot Flur homology. So the genus that I was talking about is the 3-dimensional genus. One can also consider the 4-dimensional genus or the slice genus, which is the minimal genus of a surface in B4 of genus G, where again the boundary is the knot on the boundary of B4, which is S3. And that one, it cannot tell you exactly what it is, but it gives you some bounds. And it also has applications on about surgery on nuts, which 3 manifolds are obtained by surgery on which nuts, this kind of thing. Okay, so back in 2006, in joint work with Oshvat and Sharkar, we gave a combinatorial description of this, which has the name grid homology. It's in terms of grid diagrams. And I mean, it's the same thing, but it has a different definition. So you can show that the two are isomorphic. When you construct it from grid diagrams, it's usually denoted GH. And again, there are different versions. I will explain GH plus. Okay, so what are grid diagrams? Are things like this. This is a grid diagram for the trefoil. There are n by n grids on the plane with markings O and X, such that each row has one O and one X, and each column has one O and one X. And then when we trace the horizontal segments and the vertical segments between O and X, and we always put the vertical ones on top, we see a diagram for the link. So it turns out any link has a diagram like this, and you can, once you do this, then you can forget about the link and just look at the diagram with the O's and the X's. Okay, now if you have, oh yeah, and we put it on the torus. So we identify the opposite sides of the square. Now we define a state to be an n tuple of points on the grid, one on each vertical and one on each horizontal circle. There's n factorial states. So the collection of these red points is a state. Here's another state, the collection of the blue points. Okay, so you may recognize this as being some version of Flur homology. We're going to look at the symmetric product of this torus. And yes, we're going to count rectangles. Rectangles really secretly correspond to pseudo-holomorphic strips in the symmetric product of index 1. But yes, combinatorially, we're just going to care about this kind of rectangles. So there's strip or a rectangle between the red and the blue generator, if and only if they differ in exactly 2 rows, and therefore exactly in 2 columns. And if you have this kind of rectangle and it doesn't have any other red or blue dots inside. Okay, so this is something you can count on the grid. And okay, and now, well, we didn't say anything about the markings, the O's and the X's. These are, these give you different versions. Let's just explain one of them. So you make a complex GC plus associated to the grid. It's generated by the states, by the n factorial possibilities of those n tuples on the points. And then you have to add a bunch of numbers, J1, Jn. And the differential is given by counting these rectangles. So, okay, so the differential is a sum over y. Then you look at all possible rectangles. I mean, usually there's just 1 or 0. And for this version, we're asking for the rectangles to not go through x's. Okay, and we are counting this with a sign that I'm not going to explain, but it's also combinatorial. This is plus or minus 1. And then we're putting a power of the u variables, namely this power. So yes, so u1 to how many how many instances of O1 are in the rectangle. It can be just 0 or 1. And similarly, yeah, you put a variable u for every time you see an O in the rectangle. Okay, you make a complex, and this depends on the grid diagram, but you can show that the homology does not depend on the grid diagram. This is a link invariant. And it's a module over the polynomial ring in these variables u1, un. Of course, as I said, this is an example of Lagrangian Flur homology. So what I was doing is working in this symplectic manifold, Sim and G. You have these Lagrangians. The Lagrangians are two tori. They're the product of the horizontal lines and the product of the vertical lines. I mean, of course, I'm on a torus, so these are circles. So you take the product of n circles and the product of other n circles. And those rectangles were just pseudo-holomorphic strips of index 1. And I was taking Lagrangian Flur homology. Now, of course, you know, in Lagrangian Flur homology, you have disk and sphere bubbles. Yes, if you want del squared equals 0, you'd better have this kind of thing. Now, this is okay at the level of homology. It will be so you do have this disk and sphere bubbles, but the disk bubbles cancel in pairs, and the sphere bubbles do not. I mean, the count of such things that's relevant is 0. When you just talk about homology. When you talk about homotopy, it's more complicated. So to make things less complicated, let's at least avoid sphere bubbles. And you can do that by avoiding at least one marking on the grid. So you have a bunch of X's and O's. In the version that I mentioned before, I wasn't going over any of the X's. Now you have sphere bubbles only when you have some domain that goes over the whole torus. In the symmetric product, the homology class of the torus gives you a homotopy class. It actually gives you a spherical class, and that's where you can have sphere bubbles. But if you avoid at least one marking, then you don't have sphere bubbles. So again, what you can have many versions depending on how you count the X or O markings. Now you can have disk bubbles. The disk bubbles correspond to rows and columns of on the grid. So each of these things has it basically corresponds to a disk bubble of index 2 and also a column. So this appears when you, for example, if you have a rectangle and then another rectangle going around the torus, together they can give you a row. So it appears when you do del squared equals 0. Okay. Now in homology, again, you have del squared equals 0 because the row through one O variable, through one OI marking, cancels out the column through the other OI marking. So the bubbles with boundary on the alpha Lagrangian cancel the bubbles with boundary on the beta Lagrangian. And by the way, in some versions, you don't have disk bubbles either. For example, in the version that I mentioned, GH+, because you don't have a whole row, I was avoiding all the X markings. So I wasn't, so you cannot have a whole row. But there are other versions where you want to keep track, when you want to also maybe keep track of the X markings with another variable, and then you can avoid, and then you can't avoid the disk bubbles. If you at least avoid one marking, then at least you avoid the sphere bubbles. But again, you don't have to avoid anything if you just talk about homology. Oh, someone asked, would you be able to draw a picture to illustrate why the disk bubbles cancel? If this is just an algebra cancellation, or there is an actual null cobordism between the relevant moduli space of disks. Yeah, there is a relevant null cobordism. Yeah, well, the picture is perfectly symmetric. I don't think I have to draw a picture, but the alpha and the beta Lagrangians are completely symmetric. So whatever bubbles you have on one side, you also have on the other side. Okay, so now I want to lift this to spectra. So let me just remind you. So I'm going to use the simplest version of the stable homotopy category. This is the one constructed by Spanier and Whitehead long time ago. So it's just a very mild generalization of a space. I'm going to consider objects being a space and an integer, which corresponds to a formal desuspension of the space. And the space is a pointed CW complex. Okay, and the morphisms are the stable homotopy maps between X and Y. So the co-limit as we suspend sufficiently many times and desuspended appropriately. So for example, now we can talk in this stable homotopy category by the sphere in dimension -5. Everything is based. We can talk about the homology of such an object to just be the shift of the homology of X by the corresponding n. Okay, so what I want to do is to each grid diagram and each integer, I will associate a suspension spectrum, an object in that category, whose homology is the grid homology. The grid homology, again, has two gradings. The second one is called the Alexander grading, and the first one is the homological grading. So in each Alexander grading, I have a spectrum, and its ith homology is GHI. Oh yeah, and we're doing this for the version plus, but there are other versions as well. Okay, and the homology was a ring, so it was a module over this polynomial ring, and here the action of these variables corresponds to actual maps from the spectrum in one Alexander grading to the spectrum in another Alexander grading with some suspension. Okay, now in our first paper, which appeared 2 years ago, we haven't proved that this is a not invariant. So again, at the level of homology, we know that the complex depends on the grid, but the homology is this not Flur homology, which has wonderful applications. Similarly, we expect our spectrum to be a not invariant, and we're working on it. I think we're pretty close to proving it. That's going to be a second paper if we manage to prove it, but I don't want to claim it just yet. Okay, so before I get into the construction, let me give an example of what this looks like. So here's the knot T25. This is a torus knot. You wrap 2 times in one direction and 5 times in the other direction along the torus. These are the Alexander grading, and these are the homological gradings. Yes, and each dot represents a generator in the homology of this knot. Okay, and again, sorry, no, let me try again. So each dot, this is a model for the knot Flur complex. The blue arrows represent differentials that go over O once, over some O marking. The dotted differential represent differentials that go over the X markings once, and those, let's say, we don't consider. In the version GH+, they don't matter. So in each horizontal grading, you just have, let's say, here 5 generators, and some of them are canceling in pairs, so in the end, you just have this generator. Here you also have 1 generator, just 4. Here you have 2 generators, -1 in degrees -1 and 2. Here you have 1, just 0. Here you have 2, and here you have 1. So again, the blue lines just means that the generators cancel in pairs. Now, okay, it's just a really easy exercise in stable homotopy theory is that if you have homology that's supported in 2 consecutive gradings and it's free, then there's only one possibility for the corresponding spectrum, namely it has to be a wedge of spheres. The only interesting thing could possibly happen if they're not in consecutive gradings. Okay, so in most of the cases, these are in consecutive, I mean, there's just one generator. Here, there are two generators in consecutive gradings. So basically here, this is going to be a sphere in degree 6, here a sphere in degree 4, and so on. The only interesting thing could potentially happen in Alexander degree 1, where you have two generators differing in grading by 3. So -1 and 2. And then you can think of them as cells. So it's a CW complex with a cell in dimension -1 and 2, and they're attached by some map from S1 to S-1. This is all stable, so this is an element in the second stable homotopy group of spheres, which is Zoominar. Okay, so there are two possibilities, and well, it turns out that actually the element is 0, and this is a wedge of sphere as well. Maybe I should say we didn't compute this with grids. We computed this with other Hegar diagrams, but it should give the same answer. So that's why we think that it should be 0. Okay, so I'm going to explain mostly the construction for GH+, but you can do it for other versions of grid homology, provided we avoid sphere bubbles, meaning that we don't allow the strips to cross a particular X marking on the grid. So that's all we need to avoid. The construction is going to be based on framed flow categories, which is the usual way that Cohen, Jones, and Siegel imagined Flur homotopy to work, and it's very much inspired by what Lipschitz and Sharkar did for Hovanov homology. Now, one interesting aspect is that we will need to talk about bubbles in the construction, even for the plus version, where in holomorphic geometry we don't have bubbles. But I will construct, but the construction is more concrete. So it will not involve holomorphic curves, just like the construction of grid homology. We turned it into something completely combinatorial, just counting rectangles on a torus. Our construction will be similar in flavor to that. There will be no holomorphic curves, but secretly it's inspired by Lagrangian Flur theory. And in principle, you can implement it on the computer. We haven't, well, we did a small version of that, but yeah, it's something that you can compute. Like by compute, I mean, if you want to compute the stable homotopy groups of the space. Okay, great. Are there any questions so far? Okay, so now I will go into the construction. Let me first review the Cohen-Jones-Siegel approach to Flur homotopy. Let's say we have a chain complex, and instead of the chain complex, we want to get a suspension spectrum. We first need to have a framed flow category. The objects of the category are generators of C, and the morphisms are compact manifolds with corners, M bar XY. In fact, there should be some labeling on the boundaries of these manifolds. On the strata, these are called D manifolds. I'm not going to get into the details of the right dimension. So these are models for the compactified moduli space of holomorphic strips from X to Y after we divide by the R action. And we require the usual relation that the boundary of this moduli space is the union of all broken trajectories, moduli spaces like this. And apart from all this, you need a few more things. You need embeddings of these moduli spaces into suitable Euclidean spaces with corners. So meaning you have some copies of R plus and subcopies of R, and you want these to be neat, meaning that boundaries go to boundaries and strata of codimension k goes to strata of codimension I goes to strata of codimension I in the usual. So R plus has a stratification with 0 and the positive axis. Yeah, boundary go to boundary, corners goes to corners, and so on. You also need framings of their normal bundles, stable framings. Well, actually, since I choose this embedding, just framings of their normal bundles. And you need compatibility conditions. So you have an embedding of these moduli spaces. And when you have this relation about the boundary being the union of the product, you want the embedding in here to be compatible with the embedding on the two factors in the boundary. And similarly for the framings, you want the framing on M bar when you look at the boundary to give you the framing on the product. Okay, so this is a frame flow category. This is just a definition.
Ciprian, before you move, there's a question in the chat if you want to look at it.
Let's see. Alice asked, in your setting, do you always get a framing of your flow categories, or does this require extra restrictions? Yes, in my setting, I will always get a framing on the flow category. Yes, this is because I'm doing Hegardt-Flur homology on S3 in general. In Hegardt-Flur or Seiberg-Witten, you always have framings on rational homology spheres. So if the knots are in S3, then it's fine. If you talk about more complicated S3 manifolds like T3, then you stop having framings. Okay, great. Okay, so Cohen, Jones, and Siegel explained how if you have a frame flow category, you automatically get a spectrum from it. So the idea is that you have this category, the objects are in various degrees, and you attach one d-dimensional cell for each generator in degree d. You make a CW complex in the sense of stable homotopy theory, so they can be in negative degrees. And the thing you use the spaces MXY for are the attaching maps between the cells. This is done via the Pontryagin-Thom construction. The simplest example, let's say we have two generators, Y and X, in degrees A and B, and this is K is B minus A minus 1. Then I want to construct a spectrum from the sphere in degree A by attaching a B cell. Everything is based, of course, so I have the base point and I have a cell in degree A, and I'm attaching a cell in degree B. And to do that, I need a map from the boundary, from SB minus 1 to A. Now, this is just an element in the stable homotopy groups of spheres in degree K, B minus A minus 1. And Pontryagin-Thom tells you that the stable homotopy groups of sphere is the same as the framed Bordism group in dimension K. Okay, and well, in this case, you don't have any boundaries or anything because you just have two generators. You have one moduli space, which is a compact manifold. And that's exactly of dimension K. And if you have the framing, that gives you an element in the frame cobordism group. Okay, so Cohen-Jones, so this is the simplest version. Cohen-Jones and Siegel generalize this to manifolds with corners. And they explain that if you have these boundaries and everything is compatible, then you get the spectrum. Okay, so we will do this for our complex, for GC+. For that, we need to construct, well, manifolds with corners. So these are going to be our models for moduli spaces. So secretly, we know that this is Lagrangian Flur homotopy, and we, we should have some moduli spaces with corners. We're just going to construct them by hand, inductively, in some way. Well, we need one for every X and Y, and it will also depend on the powers of U. So for every possible power of U, which tells you how many O markings you go over, you want to construct a moduli space. Now, okay, so if you have two generators X and Y, before I said that holomorphic disks of index 1 correspond to rectangles. If X and Y, have a bigger difference in index, if you want homotopy type, you need moduli spaces of any dimension. So then you won't have a rectangle, but you're going to have what's called the domain on the grid. So given X and Y, there's, and if you specify how many times it goes over a base point, to every holomorphic, actually not to every holomorphic, to every homotopy class of strips in the symmetric product, you can associate some domain on the plane. And by a domain, I just mean a sum of rectangles. So it's, I don't know, it can be something like this. Like this, it can help. You can also have higher multiplicity somewhere, and it's basically some combinatorial interpretation of the homotopy class in the symmetric, or the relative homotopy class in the symmetric product. Okay, so given the domain, yes, we put an equivalence relation on domains by saying that two domains are equivalent if they differ by a periodic domain, meaning a linear combination of row minus column through the same O. This is because we want to identify bubbles, like bubbles on alpha to bubbles on beta. So, right, so we set row equals column if they go through the same O marking. Okay, so for each equivalence class of domains, we're going to construct a moduli space. And this will be our model for the moduli space of pseudo-holomorphic strips in the homotopy class given by this, well, in the union of homotopy class given by everything in the equivalence class that we are given. Okay, so just to review, I have two generators, X and Y, and I'm specifying some powers of use. We're going to have an equivalence class. There's a bunch of domains. They need to be positive in order to support any sort of holomorphic strips. So we don't allow like negative linear combinations of rectangles, just positive or at least, yes, non-negative. So there's finitely many domains in the equivalence class. And we need to construct this manifold with corners associated to D such that the boundary is given by products of ME times MF, where E plus F equals D. So whenever you split the domain into two, you want this to contribute to the boundary of MD. And we need neat embeddings of these moduli spaces into Euclidean spaces and framings of their normal bundles. If we construct all this, then Cohen-Jones-Siegel tell us that immediately we get a spectrum.
Ciprian,
yes.
sorry, do you also need a composition? So this is called a flow category. Is it a category in the sense that you can compose morphism and composition is associative? And
right. Let me think. No, it's not.
Okay.
I mean, well, yes, you. I mean, in principle, you have that, but you don't need it to construct the spectrum.
Because this is sometimes a tricky issue.
Yes.
The
yes.
associativity of
yeah, if you want
composition.
to do gluing.
Yeah. So okay, so this.
I mean, let me put it like this. So sorry. If you have smooth structures on the moduli spaces, which we want. I mean, in symplectic geometry, it's hard to prove. I mean, okay, but here, you do have them. Then and they're compatible with everything. Then you automatically get you can choose associativity, right? So it kind of comes for free.
But it's basically an indirect argument in the sense that as a result of all the structure on the boundaries,
yes,
you can say I can define in fact some.
Yeah, basically because they come because if you want they're included in Euclidean spaces.
Yeah.
So in Euclidean spaces, it's fine. Yeah.
Okay, thanks.
Yeah. Okay, so we don't need anything else except just constructing these moduli spaces, which should be smooth manifolds with corners, and everything should be compatible. Okay, so we're going to construct these moduli spaces, one for each. So again, it's for an equivalence class. We're setting row equals to column. There can be several domains in each equivalence class. We're going to construct one moduli space for each of them. But these moduli spaces are not going to be manifolds with corners. They're going to be stratified spaces, Whitney stratified spaces with the stratification coming from this bubbling. So they're going to have a more complicated structure, and the tricky thing is to put them together. In the end, when we glue them, this is going to be a like M of the equivalence class is going to be a fine, compact manifold with smooth manifold with corners. Okay, so in order to glue these pieces, we need to keep track of these stratifications. So we need to construct not just the moduli spaces themselves, but their strata, and we're going to construct them inductively on dimensions. So we're going to talk also about moduli spaces of domains, along with a collection of these bubbles attached to them. So these are going to be called M and lambda D. I will get to them soon. Okay, let me just give you some pictures. So for example, if you have, well, if you just have one rectangle, then you get a dot. It's just the moduli space is a point. This corresponds to like index 1. After you divide by r, it's just a point. If you have two rectangles, then there are two ways of, well, it corresponds to union of, it's like a dot times a dot. It's a point times a point, which still is a point. If you go the first, you do this rectangle, and secondly, the other. Or if you go in the other direction, you have another point, and the moduli space corresponding that will construct corresponding to two rectangles is just going to be an interval between the 2 points. If you have this kind of domain, an L-shaped thing, again, this is it's a decomposition of two rectangles, and again, you have an interval. If you have 3, then you get a hexagon. These are all the possible ways of putting these domains together, correspond to permutations. These are the dots, and then you have edges, and then you have the interior. If you have bubbles, so remember every row and every column correspond to a bubble, and we want to identify them. So the row through some O should be identified with the row through some V. So in this case, basically you have two domains in the same equivalence class, the row and the column. Each of them, the moduli space I'm associating is just going to be an interval, and I'm just gluing them together and get an interval. Okay, so this is going to be the moduli space for the whole equivalence class. It's going to be the union of these things, but I'm also going to have a blue moduli space, which corresponds to this bubble configuration. So for each domain and each bubble configuration, I'll have a moduli space. If you have something more complicated, A plus B plus C. Okay, so I have a row plus a rectangle on the column through the same O. So I could replace the row by the column. And again, I have two different moduli spaces. I can glue them together and get some hexagon. And this blue thing is the moduli space of bubbles along which I glue. Okay, that was an example. A more complicated example, if you have two rows, that's equivalent to, let me see, which one is this? Yes. No, this is just two rows. I get some polyhedron like this, and I have a whole green line of bubbles with configurations like A, B, and C, D, like the bubble through the first row and the bubble through the second row. Now this, so this is for A, B plus CD. This is for the row, this row plus this row. I can replace the rows with columns, or I can have one row and one column. If I have one row and one column, then I get something more interesting. I get this pyramid, but this is a singular space. This is basically modeled on the Whitney umbrella. This is, well, just imagine that I'm pushing this face slightly into the interior, and I get some singular edge. We will see a better picture in a moment. This corresponds to two bubbles through, yeah, so this corresponds to what? Just a second. So this is, yeah, this is AB plus CD. This is, oh, I see. This is just two copies of the row. Sorry. This is, yeah, two copies of the same row. And here you can have basically two disk bubbles, and you end up with a disk bubble in the union. So this is basically when the two disk bubbles come at the same height. So you get this kind of interval. Okay, now here, if you have a row plus a column, then again you get this interval. Now you have the bubble on one side and the bubble of the other side. The interval corresponds to where the relative heights of these things are, and here is where they happen at the same side, at the same height. So basically, when I have the equivalence class made of 2AB versus AB plus CD, so 2 times the row versus the row plus the column, and also I have twice times the column, so I have two copies of this. This is the one corresponding to two rows and two columns. I want to glue them to this other picture. And the way to glue them is this Whitney umbrella. So this is the standard example of a stratified space that's interesting. You split R3 into three regions. One is this side of the umbrella, the other is this other side of the umbrella, and the rest is the rest. So, and this is the model how you glue three things along this half interval. Now, of course, okay, if you know about the Gromov compactification, this is only some part of it, so I'm ignoring some strata. Maybe in the interest of time, let me not get into that. It's a simplification of the Gromov compactification so that it's easier to glue things together. It's not exactly what you see. I mean, basically, in the Gromov compactification, when two bubbles happen at the same point, you have some new stratum of the same dimension. But anyway, this is our model, which is simpler than what happens in reality. Okay. All right, so in general, we're going to consider configurations of disk bubbles, and we just keep track of the relative heights. And the model for gluing them together is going to be some generalization of the Whitney umbrella. The Whitney umbrella is basically Sim2 of the complex plane divided by R, where you stratify according to the signs of the imaginary parts of these variables. And you can generalize this to Sim and C mod R. And you get some standard decomposition, and this is what we want to be the local model for the stratified spaces that we construct. We're going to construct them inductively, and we want to know what the local models are when we do the construction. Okay, so we're going to construct moduli spaces M and lambda D. For D is the domain, is the homotopy class in the symmetric product, and then the disk bubbles are given by, well, you specify how many there are, Ni tells you how many, or Nj tells you how many disks you have, or bubbles you have going through a given O marking. And you have a partition. So each lambda j is a partition of Nj. It's an ordered partition. It tells you that, I don't know, if the partition is 2 plus 1 plus 5, it means that you have 2 disk bubbles at one height, then 1 bubble at another height, and 5 bubbles at the next height. So for each n lambda d, I'm going to construct a space together with a neat embedding and with normal framings. And I have some specified local models given by these generalizations of the Whitney umbrellas. Okay, so how are we going to construct them? First, we construct them by hand when the domain is trivial, and when we only have at most 1 bubble through each O marking. So these are going to be just some models for the moduli spaces of bubbles at different heights, 1 bubble at most at each height. Sorry, no. Let me try again. Models for, yes, that's right. Yes, different bubbles with different heights and with different labels corresponding to the O markings. And then you just define this to be the permutohedron. This is a standard polytope. It's given by the vertices are permutations, and we give it some normal framing by hand. I won't explain what it is, but you can do that. And then embedding into a Euclidean space. It's some very combinatorial explicit procedure. And then the interesting part is that we define these moduli spaces inductively on their dimension. So we have a lot of moduli spaces for each D and for each configuration of disks. And we construct them inductively. When the dimension is 0, we just define them to be points, like 1 point for each moduli space. And we also, it's important that we also constructed these ones by hand, which were of bigger dimension. Presumably, these are already done, and the rest we're defining them by inductively on dimension. So assume we constructed all the spaces up to some dimension along with embeddings and framings. Then we want to do the next one, a k+1 dimensional space. Now, what do we have already? We have the boundary. The boundary is some union of manifolds with corners. Okay, we can smooth it. We can smooth the corners and get basically a k-dimensional framed manifold, which I call the smoothed boundary, del prime of this moduli space. Del prime is a framed manifold. It gives you an element in the frame cobordism group, which is the stable homotopy groups of spheres. Okay, so now I just want to fill it in to get my new space. So if this element was 0, I would be in business. Of course, it's not 0 in general. But basically, I'm going to construct an obstruction for it to, an obstruction for the existence of such things. And the obstruction would live in a complex, and I will show that the complex is acyclic. Okay, so great. So we're defining a complex. I'm not going to go through the whole definition. Sorry, this is a busy page. But this is a complex. It's a chain complex whose generators are positive domains with partitions. So it's the data that specify that gives us the indices of our moduli spaces. And and the differential corresponds to how how the moduli spaces get split into boundaries to the possible degenerations. So for example, the differential of a triple D and lambda has one term corresponding to subtracting a rectangle from D. This is like just a broken trajectory. And then it has type 2 terms subtracting a row or a column through D and increasing n by 1, meaning you have a bubble degenerating. So that's some other term in the differential. Then also combining two terms in the partition corresponds to two bubbles reaching the same height, and then removing a boundary degeneration when the height goes to -infinity or +infinity. So every time we expect a moduli space to be in the boundary of a bigger moduli space, we add a term in this differential, and we make a complex out of these triples, d and lambda. This is a purely combinatorial complex in terms of the grid. You just have, I mean, and it doesn't, I mean, it just uses the grid and the O's in it and the markings, and yeah, and you make a complex. Okay, and then you can compute the homology. So this is some work. The homology has rank 2 to the n. That's our computation. But we can tell where it's supported. It's supported exactly by the triples where the domain is trivial and n is made of zeros and ones. So you have at most one bubble through each marking. And then the partition, of course, it has to be just 0 or 1, depending on what n is. So you know where the homology is supported, so let's take the quotient. And then the quotient is acyclic, has trivial homology. All right, so this is some combinatorial computation that we did. Now, once you know this, you are in business. Why? So remember, we had these classes in the frame. So we're constructing moduli spaces inductively. We have the boundaries, we're smoothing them. We get an element in the frame cobordism group. We can think of this by putting all of these elements together, we get an obstruction class. So the obstruction is in the chain complex given, it's a home chain complex from CDP prime, which is our complex of triples, modulo the ones that we already constructed, modulo so this is the one that's acyclic. This is the quotient. So hum from this to omega k framed, given by OK of a triple, is whatever this class is in omega k framed. Okay, so for each triple, we have a frame cobordism class. This gives us an element in the chain complex. All right, we can prove it's a cocycle. And since it's acyclic, I mean, it kind of follows formally that it's a cocycle. If you think about how the domains break, the structure that the boundary is the product of smaller moduli spaces. So this is acyclic. So if the domain, if the CDP prime is acyclic, then the home complex is also acyclic, of course. So therefore, OK is the co-boundary of some element B. All right, so ideally, we wanted this to be 0. We wanted our obstruction class to be 0 at the chain level. If it was at 0 at the chain level, we would just fill in each boundary with some moduli space. Now, it's not 0, but it's the co-boundary of some B. So what we do is we use this B to adjust the definition of the moduli spaces that we previously constructed. So B, B is represented by some framed manifolds. On the k-dimensional moduli spaces, we're trying to construct something of dimension k plus 1. And we're just going to go back one step, kind of in the induction. And we're going to add to our moduli spaces, we're going to just take this joint union with framed manifolds representing minus b. We're just going back in like one step in the induction. We're not going back any lower. So we're not going to change the definition of moduli spaces of dimension k minus 1 or lower. Okay, so the way this works, again, is you have, let's say, moduli spaces of dimension k minus 1 and k. Now, when you constructed the ones on dimension k, you did this inductively. So you filled in the k-dimensional parts at the last step. Now we want to do k plus 1. Well, you might not be able to, but if you change a little bit the definition of the previous step by adding some manifolds, by just taking this joint union of some good manifolds, then you can. And that's what you do. So you do this inductively as you go on. This is inspired by what Lipschitz and Sharkar did for Hovanov homology. They constructed this in a similar way, and they had again some obstruction co-cycle, and they showed that the homology lives in. I mean, the homology of that was 0. Our homology was not quite 0. It was well, but if we construct the part of the moduli spaces where the homology is not 0, we construct it by hand, and then that's why we construct just the rest inductively on dimension, because this is acyclic. Okay, so right, so just finishing the inductive step, if we adjust the definition of the moduli spaces, we get that the smoothed boundary is framed null cobordant. We fill it in arbitrarily, and we get the next framed moduli space, and we continue with the induction. And the important thing is that the complex CDP prime is acyclic. Okay, now it was very delicate to arrange this. Okay, first of all, we had to avoid one X marking. I mean, in holomorphic geometry, this corresponds to avoiding the sphere, but really even the domain CDP prime wouldn't be acyclic if we go over the whole torus. Okay, we had to construct these moduli spaces where the domain is trivial and n is 0 of 1. These were constructed first by hand as the permutahedra. And finally, the most interesting point is that we had to consider bubble configurations. So even if you just look at GC+, GC+ was the version that I was focusing on, where you want domains that do not cross the X marking, that do not cross any X marking. So you cannot have a full row of columns, so you don't have any bubbles. So in principle, I could have just said, well, let's just construct moduli spaces with no bubbles, just corresponding to domains that don't go over the X's, and construct them inductively on the dimension. That would have been, in a way, easier. Like, you know, I wouldn't have had to talk about partitions, and it would have been a simpler set of indices that I would have to construct. But then I would have to work with the analog of this CDP, of the complex of triples, where we avoid all the X markings. And that gets completely crazy because it depends on the position on the X markings. And this has complicated homology. I mean, there's n factorial versions of this according to whether the X markings exist. And we put it on a computer, and it just gives non-trivial homology, and it's just really complicated, and there's no way to analyze it. But if we allow all the X markings, then we just have the grid, and we just have one complex that we have to study, and that's much simpler. And that one we show it's acyclic, well, after you quotient out by the right thing. And therefore, you can do this inductive process, and the obstruction class is 0. But of course, but then it gets more complicated in the sense that we have to construct all these moduli all these moduli spaces with bubbles, which we don't really use in the end, but somehow we need them in the inductive process. Okay, so I'm almost out of time, so let me just finish with things that are left to do. I mean, what we'd like to do in the future. So again, we're working on proving that the stable homotopy type is a not invariant. For it to be good for something, it better be an invariant. Everything we did was about versions that avoided one X marking. So if you go over the last marking, then the complex doesn't have such simple homology. It has, well, I don't know. I mean, but you can still compute it, and maybe you have to include some sphere bubbles in your moduli space. Okay, we haven't done that, but that would be interesting to do. Okay, you would like to do the same thing with pseudo-holomorphic curves, and currently I'm working with Mohammed Abu Zaid to do Hegardt-Flur stable homotopy types, and some particular case of this would be on the grid, and hopefully you will get the same answer. Now, non-trivial computations. So when I gave you the examples, everything was a wedge of sphere. So it was determined by the homology, and that's all we see so far. That's kind of frustrating, but ideally you would want to have an example where the knots have the same grid homology, but different spectra. This is kind of hard because there's not even known an example of knot-Flur homology that has torsion in its homology. So the homology is always, I mean, in all the examples we have seen is just free over Z. And it's even harder to find like non-trivial stable homotopy groups. But anyway, so the way to do this is the simplest thing that you see in homotopy and not in homology is the second Stinrod square. And this is what Lifshitz and Sharkar use for their Hovanov spectrum. And there should be an explicit formula for this Stinrod square, and this should be implemented on the computer. I think Shucharit has a student, my collaborator has a student who's working on this. And hopefully this will give some non-trivial computations. What might be easier to see is maps associated to cobordism. So first you have to define the theory. I mean, if you have a cobordism between knots, then you want to define a map between the spectra. And it's easier to see things in homotopy at the level of maps than at the level of spaces, like the Hopf map is between spheres. So hopefully once we develop the theory for cobordism, we should be able to see some interesting maps. All right, so that's all for today. Thank you.
Thank you very much, Ciprian. So are there any questions? So let's see. So there is
one in chat. Let me see.
Okay, there's
okay, after the recording ends, that sounds good.
But even before I am not in charge of the recording, but before the recording stops, we can still ask some questions, and we'll have time after the recording stops. So I have like a question that's a little bit old-fashioned, I'm afraid, Ciprian, which is that I remember from the 90s that Cohen, Jones, Siegel, and a student called maybe a student of Ralph Betts had a paper about doing a construction that would give you the actual homotopy type, not the stable homotopy type. So their construction was like this. It was, I think the conditions were stronger. The input was stronger than what you have in doing a stable flow category or a type of flow category you consider. And then the way you got a space out of it was by doing the classifying construction associated to that category. And they would show that this classifying space comes with a topology, and when you apply it, for instance, for a Morse function, they would get a homotopy type, even maybe the homomorphism type of the manifold. So this paper, I don't think was completely finalized, maybe, in the sense that I don't think it was at the end published. But there were some issues, in fact, with implementing the strategy for Morse theory.
I see. Well, is that in any way relevant to Flur theory? Because Flur theory is in infinite dimensions, and you have to, you know, I mean,
well,
indices are infinite.
It could have been relevant, but it depended what exact. So my question is this kind of distinction between this stable version, which seems completely kind of well understood today, and this other version that was unstable? Is this, you know, like, is there any progress on understanding why one version is no longer kind of, I mean, there's maybe a problem with applying this construction in the
So I'm not too familiar with this. I just have a vague memory of that.
Yeah.
I don't know, but I would think this kind of thing only is about Morse theory, and I don't know if people are studying it, but I think in Flur theory you have to do something stable because that's the only thing you can do.
I mean,
Like,
no, I mean, it's not quite true, Ciprian, because you can be in situations in which a number of intersection points, right, between two Lagrangians is finite. And yes, in principle, you would have, you know, maybe, you know, you have a lot of them, but maybe they are just in finite numbers, and maybe the degrees of each is well defined if you are like in an exact situation. And so then you can try to implement exactly this sort of okay, you can ask, okay, do you have really framings, or if are the framings only defined in a stable way? Or so that's a different question. But in principle, yeah.
Oh, I see. Maybe, but even the indices then are all positive? Like, do you consider them in negative degrees, or?
Well, that's a very good point. I mean, these are other questions one has to solve.
I see.
I totally agree with the fact that the stable version is more natural. But the point is that there was a moment when the passage from unstable to stable seemed to be more of a technical nature, having to do with some finer properties of gluing maps, basically. It seemed to be that this was the issue. So my curiosity was whether these things have now been cleared up, and I'm asking. That's why it's an old-fashioned question. It was a question that was around already in the beginning of the year 2000. So
I see. Maybe we can talk more after. I don't know.
Yeah. Oh, look. So there is some message here. So maybe I don't know what's the name of HLT. I see HLT on my screen, but I don't know who HLT is. But
maybe just to add to Octave's comments, I guess there is the Flur fundamental group, which is not a stable object.
Yeah.
So that's an example where you get some from sort of Flur data. You actually get some non-stable quantity. So I don't know if that's an analog in this case. But,
yeah. So Hiro, now, sorry, I identified you. So you want to read what or say what you to make a comment? Please go ahead if you want. No. Okay, it's okay if. So in any case, it's yeah. So my question was kind of yeah. So Claude is perfectly right. This is this feeling that there are some unstable things that one could say in certain cases, and okay, it fits with this picture. In any case, are there other questions for Ciprian maybe?